Here we're going to look at a serial connection for RL and C. R is the resistance, L is the inductance, and C is the capacitance, or resistor, inductor, and capacitor. So we are looking at what will happen when we connect these components in serial. Maybe you can remember that for the resistance there's no phase shift. It means that the voltage and the current is at the same phasor at the same angle. But for the inductor we have that the current is lagging 90 degrees if we have an ideal inductor, or the voltage is 90 degrees leading the current. And for the capacitor we have that the current is leading 90 degrees in relationship to the voltage, or the voltage is lagging 90 degrees in relationship to the current. To remember that, we have two laws, and the one in the book it says civil, and we also have a lease. For both of them, for example civil, if we have a capacitor we look at the first three letters CIV, and if we have an inductor we look at the last three letters VIL. And also up here either we look at ELI or ICE, because up here if we have an inductor we can say that first we have the voltage, because E is the electromotive force or the voltage, and then we have the current. And for the capacitor, first we have the current and then the voltage. Down here we can set here for a capacitor first the current then the voltage, and the inductor first the voltage then the current. We know from Ohm's law that the resistance is equal to the voltage divided by the current. So here we have the formula. But now we have to use vectors, because when we have an inductance we have that there's a phase shift between voltage and current, and we have to find out the resistance for the inductor, which is called the reactance. Which angle is it located? For the resistor there is no phase shift between the voltage and the current, and up here we can see all places we have that the voltage is at 0 degree, and here we also have the current at 0 degree. So for example, if we have a voltage of 100 volt and a current of 5 amp, we have a resistance of 20 ohm, and it has an angle of 0 degree. If we have an inductor, we have the reactance XL, and the voltage is the same, 100 volt, 0 degree, but the current is lagging 90 degree, so the angle for the vector of current has a direction of negative 90 degree. So if we make this calculation we have still the value for 20 ohm, but the direction is 90 degree. We also could have that the current was the reference, so we had that the current is at 0 degree, but then the voltage is at positive 90 degree, and then the reactance is still 90 degree positive when we have an inductor. For the capacitor we have that the current is 90 degree in front or leading in relationship to the voltage, so it is positive 90 degree for the current, the angle, and then we have that the reactance for the capacitor has a negative angle of 90 degree. This information we have to use when we connect resistor, inductor and capacitor in serial. We know from direct current that for a serial connection we just can add these values together, but now we have to add them as vector. So, the first situation, we have a resistor and an inductor connected in serial. The resistance has a value and a direction of 0 degree. The reactance XL has a length value and direction of positive 90 degree. And if we add these two vectors, we got the total up here. It has this length and this direction. And when we add a resistor and reactance, we have totally an impedance. So that's why we call these triangles for impedance triangle or impedance vector diagram. And this angle we call the phase shift phi. So the angle between the impedance and the resistance is the phase shift. If we have a resistor and a capacitor connected in serial, we have the resistance and the reactance for the capacitor, and totally have the impedance. We can see that the reactance for the capacitor is negative 90 degree, so the total impedance will also be at a negative angle. When we look at the calculation, we can see here, over here, impedance for R and L. We have a resistance plus a reactance added as vectors. For example, if we have a resistance of 30 ohm in an angle of 0 degree and a reactance of the inductor for 25 ohm in positive 90 degree, then we got a total of 39.1 ohm in an angle of positive 39.8. Over here with the capacitor, we have the same numbers for R and XC, of course, and totally the impedance is the same, but the angle is just negative and still the same number. Finally, we have that we also can connect resistance, inductor and capacitor in serial, and we have the resistance and, for example, a reactance for the inductor up here, and then add a reactance for the capacitor down here. And in this situation, the reactance for the capacitor is longer than the reactance for the inductor, and totally we have the impedance down here. It has a negative angle, and it could be this calculation: 30 ohm for the resistor, 20 ohm for the inductor, and 25 ohm for the capacitor, and totally we got an impedance of 30.4 in an angle of negative 9.5 degree. We also could have that if the reactance for the inductor and the reactance for the capacitor has the same length, then we can see that the impedance must be the same as the resistance, and we call that resonance. So if XL is equal to XC, though that reactance has the same length, we have resonance because the impedance will then be the same as the resistance, and up here we can just increase the frequency, though XL will be longer and XC will be shorter, and at a given frequency we have resonance, and we can calculate this frequency by this formula. The book says it's called FR, but FR we also use in electrical machinery for rotor frequency, so I prefer to call it F0. We know that from Ohm's law, if we take the resistance multiplied by the current, we got the voltage. We also can do that for XL. If we multiply by the current, we got the voltage drop across the inductor. And for the impedance for total circuit, if we calculate multiply by the current, we got the supply voltage. So we have these triangles down here. We call them current voltage vector diagram because it is a combination of current and voltage. And for the serial connection, we know that current we only have one, so normally that is the reference. And we have the voltage drop across the resistor is the resistance multiplied by the current. The voltage drop across the inductor is the reactance for the inductor multiplied by the current. And the supply voltage, or sum of these two voltages, is the impedance multiplied by the current. We still got the same angle, phase shift phi, and we can see here it is the angle between the current and the voltage. Same story for the capacitor and resistor, and over here we have the combination of both resistor, inductor and capacitor. So for the serial connection we can make these current voltage vector diagram, or we can make these impedance vector diagram, and we should know that the angle phi is the same up here for the impedance vector diagram as it is for the current voltage vector diagram. And we have two rules, either Elias or Sibyl.